please subscribe and support the channel so that we can continue to do more of the videos that can assist you. This is lesson number 2. We did lesson number 1, and lesson number 1, it did not explore into details many things. It was just an introduction, which is very important for you to know. In lesson number 1, we spoke about negative work and positive work and zero work. We said that a negative work is when an object is being displaced in the opposite direction of the force. The force is moving in the opposite direction as the displacement of an object, meaning that that force, as it moves in the opposite direction from displacement, it will do negative work, meaning that energy is going to be removed from the system. That's why we will have a negative answer, which is indicating that energy is being removed to the system. As work is a scalar quantity, it does not have a direction. So the negative, it does not tell us about direction, it tells us that energy is being removed in the system. We spoke about positive work, and positive work is when the object is being displaced in the direction of the force. Like when we apply a force on an object, the object and the force will go in the same direction, meaning that it is positive work. Energy is going to be added in the system. Then we spoke about zero work. We say that if a force is 90 degrees to the direction of displacement, such a force will do zero work. It will do no work at all. That's why normal force will not do any work, because it is acting at an angle of 90 degrees to the direction of this displacement. These questions, they sometimes ask them that why is normal force not doing work? It is not doing work because it is acting at an angle of 90 degrees to the displacement. I told you that with positive work, on our formula of work, we're going to have cos 0 for positive work. For negative work, we're going to have positive work, we're going to have cos 0. For negative work, we're going to have cos 180. Positive work, cos 0, do not cram it. Cos 0, it means 1, meaning that we're going to have our answer being positive for positive work when the force is going in the same direction as the object. Okay, so now, my opinion about teaching you work, energy, and power is that I must first explore the work done by the gravitational force. After exploring the work done by the gravitational force, everything will become easier to you because you will be understanding. So, I'm starting my lesson on talking about the work done by the gravitational force. As with the gravitational force, there are many complications and mistakes which learners make, and I want to make sure that you understand that. So I'm going to start my lesson with explaining the perpendicular and the parallel components of the gravitational force. Perpendicular and parallel components. Parallel components of gravitational force. Gravitational force. The force of gravity. In lesson 1, I told you that the force of gravity is always downward. It is a force that will always pull things toward the center of the universe. Everything is going to be pulled down. So the direction of the force of gravity is always downwards. So I'm going to focus on an incline. I'm going to talk about an incline. Let's say we have an incline which is 30 degrees, and there is a box, and this box is moving down the incline. It is moving down the incline. We'll talk about the concepts of the movement of the box later on. I just want to explain something. on work done by the gravitational force. So I'm going to start by explaining the horizontal and the parallel components. I mean the perpendicular components and the parallel component. Okay, here's the box. This box is moving down the incline. It is moving down the incline. So I want to draw a free body diagram indicating all forces acting on this box. The box is moving on its own. There's no force that is being applied. It is moving on its own. So, okay, if I draw a free body diagram, the manner in which I draw it, I first draw this line, which I'm going to erase. I draw a dot, then I draw a line. Gravitational force is a line which is vertically down all the time, whether it's on an incline or it's on a horizontal surface. I'm supposed to draw the line on the dot. Okay. Then what do I do? This is gravitational force, this is frictional force. That is frictional force. Then I'm going to have my normal force, which will be perpendicular to the surface. So this is going to be normal force. I'm not drawing applied force here because the box is moving on its own. It is not being pushed by a particular force. So the free body diagram for this, it is this one. There is no applied force. Notice that this line of normal force is facing this side. I know some people it is difficult for understanding why is it facing this side. You need to note that normal force is always perpendicular to the surface. Then the frictional force is parallel to the surface. We know that the frictional force is parallel to this surface. So normal force must be perpendicular to frictional force on an incline. Must be perpendicular to frictional force rather to the surface. So here we must have an angle of 90 degrees. That's why I'm drawing my normal line to face this side. For instance, if I drew my normal line to face up straight, it was not going to be at 90 degrees with the surface. So you need to take note that I'm drawing my normal line, my normal force, not normal line, normal force to be at an angle of 90 degrees with the surface. So that is the reason. Okay, so I want to explain the parallel component and the horizontal component. The parallel component and the perpendicular component. I don't know why I keep on saying horizontal and parallel. It's perpendicular and parallel component. Sorry for that. Okay, so I'm going to indicate the parallel and the perpendicular component. A perpendicular component, this is the component of the gravitational force which is going to be perpendicular to the surface. So gravitational force gives rise to two components. You need to understand that these components, they are not gravitational force, they are just the components of gravitational force. This gravitational force that is here, it is the gravitational force itself, it is not its component. The first component of the gravitational force is what we call Fg perpendicular. Fg perpendicular. You know that we use an upside down T to represent a perpendicular in mathematics. So this is gravitational force perpendicular. Why are we calling it Fg perpendicular? You can see that it is continuous with the Fg, with the F normal, with the normal force. The Fg perpendicular is continuous with the normal force, and the normal force is perpendicular to the surface. It means that even this Fg perpendicular will be perpendicular to the surface. That is the first component of the gravitational force. This will also give you the revision for the grade 11 forces. Okay, then we will have the parallel component. I will represent it here. Why do we call it the parallel component? We call it the parallel component because it is parallel to the surface. You can see that they are parallel. Can you see that? That's why I'm calling it the parallel component. So we have a perpendicular component and we have got the FG parallel. You know that when we want to represent parallel, just write something which looks like 11, but which is a bit skewed. We know that from mathematics. So, we have got three gravitational forces. The gravitational force itself and its two components. And these components of the gravitational force have a vital function which I want to explain to you. Okay? So this straight line, it is the FG itself. The line which is parallel like this, it is parallel to the surface. It is FG parallel. The one which is continuous with the normal force, it is the perpendicular component of the gravitational force. So what is it that these components do? Listen attentively. Look the direction at which this FG perpendicular is pointing down, meaning that FG perpendicular, if I were to draw the free body diagram directly from this box, it means the FG was going to point down FG. FG perpendicular was going to point in this direction. FG perpendicular. FG perpendicular, then, and it is continuous with normal force, Fn. Can you see that? Then, FG parallel, it is going to be parallel with the surface. It is going to be parallel with the surface or parallel with the applied force or frictional force, since they are those forces are parallel to the surface. Can you see? It is pointing this side. Some they prefer to write it here. I'm writing it here so that I can explain, so that I can form triangles, so that I can explain what is happening with this triangle. So FG parallel is pointing where the object is going. Okay. So look at these two. Let me use this book to explain. FG perpendicular is pressing the object down. Isn't it the object is on an incline like this? FG perpendicular is going to press an object down. As you can see, it's a force which is what? Pointing down. So FG perpendicular will press the object down. And pressing the object down, FG perpendicular causes the object to be firm on the ground and not move. Let's say I'm using this marker. This is the incline. Then the marker is here. So, to prevent the situation where this marker is moving down the incline, FG perpendicular is going to press this marker to attach to the surface, you understand? To prevent it from moving. That is the function of the FG perpendicular. It presses an object to the ground to prevent it from doing what? From moving down the incline. Okay, I think I can write that so that you take some notes. FG perpendicular prevent an object from moving down the incline. Sort of FG perpendicular becomes a glue that will glue the object to the surface of the incline. FG perpendicular is going to glue the object on the surface of the incline to prevent it from moving. I'm still coming. Then let us talk about FG parallel. Let us talk about FG parallel. FG perpendicular presses an object to attach more to the incline so that the object does not flow, does not just move on the incline. Let us talk about FG parallel. What does the FG parallel does? FG parallel. You can see that the FG parallel is pointing down the incline. FG parallel is pointing down the incline. What does that mean? It means that, since our incline is like this, it means that FG parallel is tracing an object to move down an incline. As you can see that FG parallel is pointing down the incline. It is parallel, but it is pointing what? Down. So FG is tracing an object to move down. FG parallel is tracing an object to move down. But FG perpendicular is tracing an object to stay there, to get attached to the surface of the incline. You see, that's why FG perpendicular, FG perpendicular, I hope I didn't confuse you. FG perpendicular is pressing an object to be attached to the surface. FG perpendicular is pressing an object to be attached to the surface of the incline so that it does not move down. But FG parallel, it is parallel to the what? It is parallel to the surface. It is tracing an object to move down an incline. You understand? I hope you now know the function. FG parallel stress the object to move down the incline. To move down the incline. Because FG parallel is saying move down to the object, move down, it is stressing it. But FG perpendicular is fighting FG parallel, it's saying don't move down, get attached to the surface. Get attached to the surface. So FG parallel and FG perpendicular, they're not friends, they're fighting. FG perpendicular, you can see, it is causing an object to be attached to the surface by pulling it towards the surface that attach here. But FG parallel is doing what? It's saying to the object, move down. So they are stressing each other. This is FG parallel and FG perpendicular. I was first explaining. Let me explain the situation where we are calculating these two forces. How do we calculate FG parallel and perpendicular, and why? Why do we use sine for this one? Why do we use cos for this one? Okay. So now I've explained their function, FG parallel and FG perpendicular. Sometimes you find that it's a car, it's a taxi which is on the incline. It's a taxi which is on the incline. And you see that. You find that the owner of the car leave the car on an incline like this, in the pegging like this. Sometimes you will hear that there was an accident of a car which moved on its own without the driver. So this can be explained by FG parallel and FG perpendicular. Since what will cause this car to stay here and not move is the braking system of the car and also FG perpendicular. FG perpendicular will be pulling the car down, but the car must not move. FG perpendicular will be pulling the car down, that the car must not move. Yes, it will pull it in this direction, that the car must not move. The car must not move. But FG parallel will do what? Will stress the car to move. If FG parallel is much more stronger, that it can overcome the braking force and the FG perpendicular. It means the car can move on its own. That's why you find that the car it can cause an accident while it can just flow down the incline on its own, because FG perpendicular, FG parallel was stressing the car to move down until it succeeded. It overcame the braking force. So FG parallel is always there, stressing the car to move down, but FG perpendicular will just hold the cat down and the brakes. You understand? So that situation where a car is moving on its own, on an incline or on a steep slope, is because of FG parallel and FG perpendicular. That is what is happening. So now, when we calculate FG perpendicular, we say FG. Okay, let's start by explaining FG, the gravitational force. Gravitational force is first to weight. Weight, which is the product of mass and gravitational acceleration. We know that gravitational acceleration is what? It's 9.8 meters per second square. It's 9.8 meters per second square. Meaning that the gravitational force, which is equal to the weight, is equal to the product of the mass of the object multiplied by the gravitational acceleration, which is a constant. It does not change. It's 9.8. We also use it in the work, energy, and power. So this is the formula for gravitational force. Which one is gravitational force? This line, not its component. Gravitational force itself. Gravitational force itself, it is equal to the work, not the work. It's equal to the weight, not weight. It's equal to the weight. The weight, which is equal to the product of the mass of an object, and then gravitational acceleration, which is a constant, 9.8. So this formula of calculating the gravitational force leads us to the formula of calculating the component of the gravitational force. You can say FG parallel. FG parallel. Look what will happen to FG parallel. FG parallel, we say, is the product of mass and gravitational acceleration sine theta. I will explain why we use sine. Then FG perpendicular is equal to mass of an object multiplied by gravitational acceleration, then cos theta. Do you see this triangle? You can see this triangle, right? I hope you can see that triangle that I have represented for you. And here we have 90 degrees. This is 90 degrees. I want to explain because this triangle is very important for you to understand that for gravitational parallel, the one which is pressing an object to move down and incline, we use sine theta. For gravitational perpendicular, the one which causes an object to be attached to the surface, we use cos. Why is that? I usually tell kids that the triangle have changed its direction. What do I mean when I say the triangle have changed? Okay, look at this. I'm going to leave that so that I use it to explain. Let's say I have this Cartesian plane. Then I draw this triangle. I draw this triangle. Let me just say that the longest side is 6 units. Then this one is 4 units. This one is 3 units. This one is theta. This one is 90 degrees. And you see that. You can see the triangle. If this one, we call it x. This from the trig ratios. We call it x. This one is y. This one is r. For trig ratios, we usually do not use the hypotenuse, adjacent, and opposite. We use x, y, and r. We know that cos theta equals to x over r. Sin theta is equals to y over r. So the use of cos and sine with calculating the parallel and the perpendicular component come from here. I want to show you something. You can see that this triangle, the way it is different from this one, this one, this one. Okay, let me explain to you. Right? Let's say we want to find cos theta of this triangle. Cos theta for this triangle will become, cos theta for that triangle will become cos theta is equals to x over r, which will become x is what? Is 4. R is 6. So cos theta for that triangle will become 4 over 6. Can you see? Cos theta is 4 over 6. Okay, let us check sin theta. Sin theta for this triangle will become y. What is y? Y is 3. 3 over 6. Y over r. Can you see? For this triangle, cos theta is going to be 4 over 6. Sin theta is going to be 3 over 6. You know that sine is y over r. You can see this, right? Okay. Let's say we were to shift this triangle. We take this part to come here. Meaning that this x will become y. Let me do it. I shift the triangle to come this side. I take the very same triangle. What do I do? It means here I will have 3 because this part since it is vertical, it is going to become horizontal. Then this one is horizontal. It is going to become vertical, meaning that here I will have 4. Then theta will be here. Here we will have 6. Nothing has changed. Okay, let me erase this so that you can see. Okay, it's important that I write this so that you can see. Sine was what? Sine theta is equals to y, is equals to 3 over 6. Okay, I want you to see something. We take this triangle, we shift it to become like this. It's the very same triangle. You can see that this y will become x and this x will become y. Can you see? We just took it like this. We put it here, shifted it like that, the very same triangle. So let us find cos. Cos theta for this triangle will become what? Cos is x over r. Cos is x over r. Let us check. This one is for the first triangle. Let us check for this second triangle. Let me write here. We're going to have cos theta x over r. Cos theta will become x is 3 this time. 3, r is 6. You see for cos of 3 over 6. Then for sine, let us check. Sine theta is equal to y over r. Let us check. Which one is y? Y is 4. We're going to have 4 over what? 4 over 6. Okay. Let us compare the two. At first, cos for this one, when the triangle is here, cos is what? Cos is 4 over 6. But when we shift the triangle, cos is 3 over 6. Meaning that, look at it, 4 over 6 for this triangle is sine. For this triangle is cos. So, that is the reason for the parallel and perpendicular components. We have opposed, we are using, for parallel we use sine, for perpendicular we use cos. It's because the triangle is shifted. It's not like this when we try to calculate. So that this is the reason for where we are opposing. I don't know if I make sense. Although you don't need to understand this is just explaining for you to understand why. You can even claim that for perpendicular we use cos theta, for parallel we use sin theta. You can even claim, but this is the explanation. Sometimes some of the things we understand through claiming. Yes, I promote that we claim some of the things. Yes, but I've explained if you are interested for you to understand. You can see that this is what is FG parallel. This triangle, you see, this is the Cartesian plane, this one. So this triangle, it looks like this one. That's why cos will become sine. You can see that sine is 4 over 6, and this side 4 over 6 is cos. Between this triangle and this triangle. So that's why for perpendicular we use sine, for parallel we use cos. Okay. I hope you understood what I was trying to show you. I hope you understood. I was trying to show you the perpendicular and the parallel components of gravitational force. We can try to do an example. Let's say we have an incline which is like that, and the box is on that incline. The incline is 80 degrees. The box is 2 kg. Calculate the parallel component of gravitational force. Okay, let me just draw them. Note that I drew those components for the sake of explaining. I don't encourage you guys to draw these components when you are asked to draw a free body diagram. Draw the main forces, don't draw the components, because the marking for components is very strict. So it's best that you draw the forces themselves. But if you are comfortable, you can do it, but I don't advise it. So for this one, FG, how do I draw FG? FG, you draw a straight line down all the time. Whether an object is on an incline or is on a horizontal surface, you draw a straight line, a line which is vertical down. FG. Then the line which is going to form 90 degrees for normal force with the surface. It must face this direction. I didn't just decide to choose that it must face this direction. No, it's because here I must have an angle of 90 degrees. I must have an angle which is like a corner. Normal force and the surface, they must have an angle which is like a corner, right? The second thing you need to note, I'm just drawing this free body diagram here on the incline so that I can explain this. When you draw a free body diagram, you must never ever draw the other things. You draw forces only. I'm drawing them to explain. That's I'm drawing on the top of an incline. Okay. Then I'm going to have the what? The FG perpendicular. Then I'm going to have the FG parallel. So let's say I want to calculate FG parallel. FG parallel for this object, I'm going to say MG, it is parallel. It means I use sine theta. So this is the gravitational force parallel. Remember that the parallel, it is tracing an object to move what? Down the incline. Then the perpendicular, it is causing an object to speed to the surface to avoid moving down the incline. Take note of the two. Then I'm going to say the mass, which is 2, gravitational acceleration 9,8. I said it's 8 here. Then sine, the angle of the incline is 80. Then I'm going to get my solution like that, which you may write here, and you give us the solution. If I want to calculate the MG perpendicular, I'm going to say MG cos theta for the perpendicular one, gravitational force perpendicular component. I use cos. You can learn or you understand, as I've already explained to you. They will never change. For parallel, you use sine. For perpendicular, you use cos. Parallel is traces an object to move down. Perpendicular, it causes an object to stick to the object, to stick to the surface. What am I saying? Then here we're going to have 2 multiplied by 9,8 cos 80. Then we get the answer. Which we are going to write. Because for now, I'm not interested in answers, but explaining how these things function. I hope you are understanding what we are doing. So take note of this. Okay. It's a bit of revision of the forces, but my aim is to do an energy and power. So I love the work done by gravitational force. So now, since I've explained the gravitational force, did you know that gravitational force sometimes can act as a friction? It can act as a friction. It can act as an applied force. Look, what will happen? If an object happens to move down, it is moving down the incline, right? FG perpendicular is doing what? It's acting as a friction. You notice it is pressing an object to stick to the ground, and it becomes very difficult for an object to move down because this gravitational force, it is opposing the motion of an object. Do you see? When the object is moving down, FG perpendicular is opposing the motion of an object. Do you see that? Then when an object is moving up, FG parallel, you see what FG parallel is doing? FG parallel, remember FG parallel is pointing down. So when an object is moving down, is moving up, FG parallel is doing what? It's opposing the motion of an object. It is pressing an object to move down, meaning that FG parallel, it becomes friction. It becomes friction in the sense that it opposes the motion of an object. Do you understand what is happening? Yes, but I'm using the word friction for the sake of explaining, guys, because when we come to the physics law, I can't say that gravitational force is a friction because gravitational force perpendicular is what? Is parallel to the surface. So, and remember that friction is a force which opposes the motion of direction of an object and act parallel. The only force which can be friction, I can boldly say that it is becoming friction, is gravitational force parallel. When an object is going up, this gravitational force parallel, components parallel, will be acting downwards, meaning it will be stressing an object to move down. You understand? So I hope understand those concepts. Okay, I'm about to explain the second one. Okay, we're back at it. Now, I want to talk about the work done by the gravitational force. Since I was still explaining components of gravitational force, I'm very conscious of what I'm doing. I know that I'm teaching gravitational force. It is intentional. You need to understand everything about gravitational force because it's the only thing that can give you problem when you are dealing with work, energy, and power. So, I know in the first lesson I explained work. You know what work is. Work is what? Is the product of the force and the displacement of an object. Because theta, which is the angle between the force and the displacement of an object. So work is force multiplied by displacement multiplied by cos, the angle between the force and the object, and the displacement, the force and the displacement. So displacement, it simply means the distance that an object moves, the distance that an object moved when the force was being or when the force was acting on an object. Displacement is the distance that an object moved when the force was acting on the object. So yeah. So now I want to still continue with the work done by gravitational force, and of course on an incline. There are three types. There are three types of work done by the gravitational force on an incline. There are three ways of calculating it. Actually, it's two types. I'm saying three because there are three methods. There are three methods. The first method is the one of using the components to calculate the work done by the gravitational force. The second one is using this formula as it is. Then the third one is when we are not given the parallel displacement, but we are given the distance above the ground for the incline. which is very important. It was intentional for me to explain those components of the gravitational force, because when an object is moving, let's say we have an incline, when an object is moving here, which gravitational force is playing a role? It is the FG parallel. Remember I said the FG parallel, it is the one which stresses an object to move. So FG parallel is the one which is playing a role in ensuring that the object moves. So it means whenever we say gravitational force, we will not be talking about the gravitational force as FG in this situation when the car and box move down, but we'll be talking about the FG parallel. Understand? When an object moves down and up the incline, we're talking about FG parallel. We'll be calculating FG parallel, but we call it FG in silent. But I'm teaching you today that whenever you hear us talk about gravitational force on this displacement, let's say I said that a car has moved, a box just was displayed 5 meters on this incline. Just know that the force that is here is not gravitational force alone, it's the gravitational force component, and that is the gravitational force parallel component, because the parallel component, it is the one which will end as the object is moving up and down. It is not FG itself. Understand? If I ever say this, let's say I say the object here is 5 meters. The object moves from this point to here, and this is 5. From this point to the ground is 5. I will not use the gravitational force parallel. I will not use cos, I will not use sine. It means I will be using the what? The gravitational force itself. The gravitational force itself. The gravitational force which is given by Fg is equal to weight, which is equal to mg. It means the gravitational force itself. Here, for F, I will use mg. I will not use a sine or a cos, because this displacement affects the gravitational force itself, not the component. I hope I'm bringing something. I hope you are understanding. Look at this. If this is a box, right? If this is a box, it's very important for you to understand the relationship between the force and the displacement. Look at it. If there is this is gravitational force, right? No, remember that when we draw a free body diagram, we draw a dot, we draw a gravitational force, right? Then there is frictional force, Fg. Then there is a normal force. The object is moving by itself in that case, then frictional force. We draw a free body diagram like this. I'm doing this intentional so that you don't make mistakes. I'm drawing my free body diagram here so that I explain for you to understand. Since I'm not just teaching a free body diagram now, I'm explaining this concept. But when you draw a free body diagram, you draw it like this. There must not be any additional line. No additional line. You draw it like this. Only the forces that are acting on the object. No additional line. So don't do what I'm doing when you are asked the question. I'm doing this so that I can explain. Fg, not the component, Fg itself, right? Then normal force. Then no, my normal force is wrong. You must face this side. You see, how did I notice that it was wrong? It was more than 90 degrees. It was more than 90 degrees. So it must be 90, it must form this 90. Like a corner, you know, a corner. This is a corner. It must form a what? A corner. So yes, normal force. Then I'm going to have Fg perpendicular, and I'm going to have Fg parallel. Fg parallel. Understand, right? So I want you to notice something. This is, let me explain. This is Fg perpendicular. Then this is Fg FG parallel. See, it is parallel to the surface. I want you to notice this about gravitational force and the displacement. When an object is displaced here, it is moving here in this surface. You see this surface? It means when we say calculate work done by the gravitational force, you are calculating work done by the gravitational force parallel component, because the object is moving here on this surface. The gravitational force that is acting here on this displacement, let's say that you are given 5 meters. You see, this 5 meters is for which displacement? It's for here. Meaning that if you want to use this 5 can only work with the what? With gravitational force parallel. Understand? You can't use gravitational force perpendicular or use gravitational force itself like mg. No, it won't work because this displacement is here. So this displacement works with fg parallel. You can see the parallel. So it means fg parallel will work from here to here. You find that in another question. You are not given this displacement, you are given this one. You are given which one? This one. 5 meters. Look at the displacement that you are given. You are given this one. And this one is parallel to which one? It's parallel to this Fg itself, not its component. Fg itself, meaning that when you calculate the work done by the gravitational force, you are going to use Fg itself as a force in this displacement. Meaning that you are going to, for Fg, isn't it? Work done by gravitational force is going to be F delta x cos theta. Meaning that for that one, we're going to say F mg, then 5 cos. The object is moving down. The object is moving down. When it is moving down, it is doing positive work because gravitational force is always downward. And the object is moving down, meaning we're going to have cos 0. I will explain this cos 0 into more details after by doing a question. This is just an explanation. You see, when I'm given this displacement, I use mg itself. But when I'm given this displacement, if I want to calculate the gravitational force, the work done by the gravitational force, I'm going to say work done by gravitational force is equals to mg sine theta cos delta x cos theta. I know some people do not use this formula. It's fine. I'm going to explain both now when I give you a question, explaining all of them together. Look, notice here I'm having mg sin theta. What is mg sin theta? The parallel component. Then I'll get the work done by gravitational force. Because I'm given this displacement. This displacement work with mg parallel. Okay. Maybe I'm enlightening something to you. Maybe I confused you. I don't know. Okay. Now let me do a real question. I will use all methods. The 3 methods. Okay. Let me draw. Here is an incline. We have a cart. This cart. Okay. You know we are not people of arts, but science and maths is art. That drawing there. Okay. 30 degrees. The incline is 30 degrees. As you can see, the cart is moving down. The cart is moving down. The displacement is 1.5 meters. It's moving down and incline. The displacement is 1.5 meters. The mass of the cart is 2 kg. The mass of the cart is what? It's 2 kg and it is moving down the incline. It's moving down the incline. Let us use the 3 methods. Let us use the 3 methods of calculating the work done by gravitational force. Let's use the three methods for work done by gravitational force. Okay. Here is the first one. The first one, it is usually discouraged by our curriculum heads because it confuses kids, because kids will need to use sine, they later on use cos. Let me start by the one which I want you to use. But after all, I don't have a choice. You can choose what you want. I'm going to start by the one which I prefer kids to use. Here is the note for this one. Number one, when an object is going down, we use theta. We use theta is equals to, that's fine. We use theta as theta is equals to 90 minus incline angle. Can you see that? When an object is going down, we use theta is equals to 90 minus incline. Which theta am I talking about? This theta. Since this is force displacement, cos theta, we use 90 minus incline. Meaning, since this object is going down, we're going to have our theta as 90 minus 8. Theta is equals to 60. So we're going to use 60. And we use the formula as it is. We do not change anything. So, number two, when an object is going up, we use theta is equals to 90 plus incline. Guys, this is what we need to think. That's why when I'm writing, it does not look much more like physics. Even physicists may refuse for us to explain like this, but it is true. It is true. Meaning that theta is going to be 90 plus 80. And theta will become 120 degrees. When the object is going up. Consecutive will get a positive value. Then cos 120 will get a negative value. Positive work, meaning that energy is going to be added in the system because of gravitational force, because the object is moving down the incline. The displacement and the gravitational force are on the same direction. I was saying to you that we've got two ways of solving this kind of questions. The first one, I told you that when an object is going down, for theta on this formula, theta becomes 90 minus the angle of incline. The angle of incline, the inclination here. Then when the object is going up, theta is the 90 plus the angle of incline. When the object is going down, is theta minus the angle of incline. When the object is going up, theta plus the angle of incline. I hope I did not confuse you. When the object is going up is 90 plus theta. Theta, I'm talking about this one. Let me write incline. Then down it is 90 minus incline. Understand? So with this case, the object was coming down. The object is coming in this direction. So how do we calculate the work done by the gravitational force? We are going to use the same formula, which is this formula. Use this formula. It means that we'll be going to be specific this time. Work done by gravitational force. Notice that I do not write work. I write WFG is equals to FG multiplied by displacement of Fg, and since the object is moving on this surface, it means the FG which is making an impact here is the FG parallel. You'll see when I use the other formula. So it means here I'm going to write as FG, which is mg delta x cos theta. I encourage you to use this type of working because this one is straightforward. You don't introduce sine and cos, but it depends on how your teachers taught you. Because teachers teach differently, and you must stick with what your teacher teach you, because that's how that's the best thing you can understand physics, and you must believe in your teachers. That's why I'm going to use both methods since we are taught by different teachers. So here we're going to have the mass of an object which is equal to 2, gravitational acceleration 9.8, displacement 1.5. Then cos theta. Since the object is going down, we're going to have 90 minus 8. 90 minus 8, which is this 8. So it means we're going to have 2 multiplied by 9, 8 multiplied by 1, 5 cos 60. Cos 60. Then when we multiply everything, we're going to get 14,7 joules. Since we are dealing with work, 14,7 joules, there's no direction. It's a scalar quantity. I hope you now understood. So now we can try to explore the other method. We can try to explore the other method. I wanted to erase that part, but I won't. Okay. How do we deal with the other method? The other method, I'll write it here. The other method is easy. Since the displacement is here, and I told you that the force which is pressing an object to move down, it is the gravitational force parallel, FG parallel. So it means we need to calculate FG parallel. The force on this formula, this FG is FG parallel. So we're going to say work done by FG is equals to FG parallel, then delta x cos theta. The question now is how to calculate FG parallel. I showed you initially. FG parallel, we will have mg sine theta delta x then cos theta. That's how we move. You can see this is FG parallel. Why are we using FG parallel, not perpendicular? It's because the object is moving on this surface and it is moving downward or upward. The force which stresses or affects an object as it moves up or down the incline, it is the one FG parallel. Remember, FG perpendicular causes an object to stick to the surface. So we will use FG parallel, whereby we're going to have our mass, which is 2, gravitational acceleration 9.8, sine. Our theta is 8 sine theta, then the displacement is 1,5. Then cos, we no longer use this, we don't use a 90 minus theta thing. This time we're going to use, is it positive work or negative work which is being done? The object is going down. So this is positive work. Remember, for positive work, we use cos 0. So it means we're going to have cos 0. If the object was going up, we're going to use cos 180. The reason for that is to have negative 1 and positive 1. Cos 0 is 1, positive. Cos 180 is negative 1, negative. So how do we know if we are supposed to use 180 or 0? We check if we've got positive work or negative work. The object is coming down, as you can see. Gravitational force is always downwards. So it means that this is positive work. The displacement and the force, they are in the same direction. So we're going to use cos 0. When the object is going up, the displacement is upward. Then the gravitational force is always downward, meaning that the displacement and the force that are moving in opposite direction, negative work. We're going to have cos 1 each. So that is the reason. So surely with this, we are going to get 14,7. Let us put that to the test. 2 multiplied by 9,8 multiplied by sine 80 multiplied by 1,5 and multiplied by cos 0. Let's see. Exactly. We get 14,7 joules. So you see, these are two methods. I hate this method because you use sine and you use cos. You see, sine and cos at the same time. Sometimes it can confuse you as a learner, but I was taught using this method when I was doing my grade 12. So I got used to this method, but on myself, when I was doing physics by myself now as a teacher, I started to love this one because this one is straightforward. There's no sign, there is no calculating work done by FG parallel. You just calculate the work done by gravitational force straightforward without changing this formula as it is. So this one we change the formula. So yeah, these are the two methods to calculate the work done by gravitational force. So I was telling you that we have got many different ways of calculating the work done by the gravitational force. These are the two methods. Let me show you the third method. Let me show you the third method. You will see how we deal with the third method. But the third method depends on how the question is formulated. So I'm going to formulate another question and I give you a chance to look at it. Okay. So let me show you now. Let's take let's say you are given a question like this. There is an incline. Let me use 20 now. 20 degrees. There is a box. There is a box. Then you are given the height of the incline, and that height is 5. You are given 5 as the height. Notice that you are not given this displacement. You are not given this displacement of the surface where the box is. You are just given the height. You are told that the box is moving from this point to this point. So you are given the what? The height. You are given the height. The box is moving. It was just captured or drawn when it was here, but it is coming from this height. Calculate the work done by gravitational force. You need to notice that formula of using sine will not work because you are not given the displacement. This formula, Fg work done by Fg is equals to mg sine theta, then beta x cos theta. This formula will not work because this is the formula for the FG parallel, and FG parallel, it will exist from this point to this point. FG parallel, it will exist from this point to this point, and they are not given the displacement from this point to this point, meaning this formula will not work. You do not have the displacement from this point to this point. This formula only works with the displacement when you are given the parallel displacement. If you are not given the parallel displacement, it will not work. Okay, so what is the formula that is going to work? Which formula are we supposed to use? Let me show you. It means this time around, we will not be calculating the work done by any component, but we will be calculating the work done by gravitational force itself. If I were to draw a free body diagram, I will draw it here for the sake of explaining. I repeat, don't draw a free body diagram on the diagram. itself when you are asked a question. You only draw forces. I'm drawing it here to explain to you. So if I were to draw a free body diagram, I'm going to draw a dot there. I'm going to draw a straight line which is parallel to this one. This line is parallel to this one. Then my normal force is pointing in that. Why is it pointing in that direction? It's not the matter of I just choose where I want it to point. No. Normal force is perpendicular to the surface, meaning that the normal force and the surface, the surface is that part where the object is moving at, and the normal force, they must form what? 90 degrees, this 90 degrees. 90 degrees, that is a corner. 90 degrees, that is a corner. So yes. So now, this is what is going to happen. You can see that we are given this displacement, meaning that the gravitational force is going to act from this point up until this point. In terms of displacement, the gravitational force is going to affect this object as far as displacement is concerned from this point to this point. Meaning that if we want to calculate the work done by gravitational force, we will not calculate the work done by any component, but we will calculate the work done by gravitational force itself. So this is what we're going to have. We're going to have we're going to have work done by Fg, and this Fg itself, it will be Fg multiplied by displacement multiplied by cos theta. Notice we are using this formula because we are given this displacement, which is, it won't be delta x, it will be delta y. Since you can see it is in the y-axis, this value. Then delta x will not work because delta x is this one. Understand? Then we'll have work done by gravitational force, which is mg delta y cos theta. Mass of an object, is the same object as I gave you initially. The mass is 2 kg. I forgot to indicate the mass for you. The mass is 2 kg. So we're going to have mass 2, gravitational acceleration 9,8. This is delta y, I'm sorry. Delta y. Then we'll have cos. Is it negative work or positive work? Is it negative work or positive work? The object is coming down, it is positive work. Why am I saying positive work? The object and the gravitational force, they are moving in the same direction. Rather, displacement is in the same direction as the force. So I'm going to use cos z. Then my answer is going to become 2 multiplied by 9,8 cos 0, which will give me 19. No, I forgot to write the displacement. This displacement, I forgot to substitute it. It's 5. Then cos 0. Those are kind of mistakes that we make sometimes. We must correct that. 2 multiplied by 9,8 multiplied by 5 and cos 0. Cos 0, it will give me 98 joules. So notice how we have used our formula. We use delta y and we use mg without having a sign, without having anything. This is the weight. It is the weight as it is originally. So why are we using this formula? Because we are given this displacement, the upwards displacement. You understand? That is how we can solve that one. Another thing we need to notice is that work done by gravitational force is equals to the change in the gravitational potential energy. Potential energy. This is something that I can just share with you for you to know. Although I don't love exploring this, but it exists. It is also correct, meaning that you can calculate the gravitational potential image, EP, gravitational potential energy, which you can say mass, which is 2, 9,8 multiplied by height, that is the height, 5. And you can see why having 2, 9 multiplied by 5, this will give us a y, meaning that even the answer here will be 9,8 joules. You understand? So that is one of the methods we can use to solve the work done by gravitational force. The work done by the gravitational force is the same as the change in the gravitational potential energy. So yeah, so this is correct. This is the product should have subtracted the 0 there. So yes, this is how we calculate the work done by gravitational force. So in the third lesson, then we'll come back to doing the work energy theorem, explaining work net and everything. Then we'll be moving toward the end, finishing this topic for work energy and power. But I know the main problem with work energy and power is calculating the work done by gravitational force, which we are done. So we'll just go and do the work energy theorem in lesson number 3. Then it will be easy since we've already exhausted work done by the gravitational force. Then we'll be done. Don't forget to subscribe to this channel, to support this channel, so that we can be encouraged to make more videos. Go to YouTube. When you are on YouTube, search Butomi Bila, then my videos are going to come. Subscribe, support the channel. All topics, grade 12 for physical sciences, they are uploaded, they are there. You can watch it anytime. We want you to pass and make a difference in the community.